Hi, I'm Sarah. Today I'd like to introduce you to our work on benchmarking object detectors under real-world distribution shifts in satellite imagery. Deep learning has achieved remarkable success in various day-to-day applications, such as in airports, healthcare systems, and damage assessment. However, these models are designed based on the IID assumption, where it is assumed that the training and testing set comes from the same distribution. However, when the models are deployed in real-world settings, we often observe a significant performance drop due to the difference in the source and target distributions. This problem is known as domain shift. So domain generalization aims to bridge this gap caused by domain shift without using target data during training. However, we noticed that standardized benchmark datasets specifically designed for assessing object detection under realistic domain generalization scenarios is currently lacking. In this work, we focus on spatial domain shift in Earth observations. Let's take this as an example. We would like to identify buildings from satellite imagery. Our training dataset consists of two source domains, data from Greenland and Madagascar, and we hope to deploy this model somewhere else, such as in Qatar. To our eyes, there is a distinct difference between the images from the target and the source domains. And these are kind of influenced by factors such as, natural landscapes, differences in climate zones, and economical developments, and so on and so forth. These shifts are also intensified by the fact that we have limited data sets for underrepresented areas during training, and by the environmental conditions that kind of vary unpredictably. So in this work, we propose a novel and realistic and challenging suite of data sets designed to evaluate the robustness of modern object detectors called RWDS. We also provide an in-depth analysis on the performance of these state-of-the-art models on this data set. Finally, we analyze the impact of two different training schemes, such as training on a single source versus training on multiple source setups. So the first data set that we propose is called RWDS across climate zones. Here we use the Köppen climate classification system, and we select three distinct climate zones, such as climate zone A, which is tropical, climate zone B, which is dry, and climate zone C, which is the warm climate zone. And to create the dataset, we use the raw satellite imagery from XView. To create the domains, we first map the coordinates of each raw image to its respective climate zone. We split the overall dataset into domains. And when we do that, we face an issue of mismatched classes across the domains. To resolve the issue, we retain classes that appear in all the domains, so in all the climate zones. And we also set a threshold of 30. And any class has samples below that, we drop it from the training. This yields our RWDS climate zones dataset. To create the splits across training, validation, and test, we follow algorithm 1. This is important because we are splitting based on the instances rather than images, given that the problem is an object detection problem. In addition to climate zones, we look at disaster damage assessment, and this is important because of climate change, and climate change is increasing the frequency of natural disasters. And tackling or having a robust object detector is important in this specific application because it's often used to support aid delivery and guide building reconstruction efforts, in addition to providing government and humanitarian agencies with an estimate of the disaster's impact. In particular, we look at flooded regions, and here we kind of examine the shift of the same disaster type across distant geographical regions with different socioeconomic characteristics. In particular, we look at floods that occurred in the US versus India, and we use the raw images from XBD dataset. Also, we study disaster events due to hurricanes, and we focus on hurricanes that have occurred in North America. And the main difference between this and the flooded region is that the disasters here are closer in proximity. And we focus on hurricanes Florence, Michael, Harvey, and Matthew. To create the dataset, we map the geolocation of each of the raw images to the country, region, and continent it belongs to. We convert the polygons, since XBD is a segmentation dataset, to the bounding boxes. We extract images for each of the two datasets I've mentioned, The first based on the hurricane events, and the second is based on the location. And when we do that, we face an issue of data imbalance between the domains. Now, XBD consists of 4 classes. To resolve this imbalance, we convert the problem into a binary problem. So we end up with damage to no damage classes. And then we follow the same algorithm 1 as we've seen for roads across climate zones to split the instances among training, validation, and testing splits. So to summarize, in roads, we propose roads across climate zones, roads across flooded regions, and roads across hurricane events. And when we projected the images into the latent space, we observed that ideally, if the data or the domains were very similar, you would expect them to overlap. And here, because there is a shift, we see that they define or they create very well-defined clusters. And this is valid for the 3 data sets. In terms of training scheme, we have 2 separate training schemes, the single source and the multi-source. In the single source training, we train on data from one distribution, whereas in the multi-source training, we train on a combination of source domains, each with a different distribution. And we always leave one domain out, which we use for an OOD testing purposes. The evaluation matrix is used. We use the mean average precision, the harmonic mean, and the performance drop. And we evaluate classical object detectors such as FASTER RCNN and MASC RCNN, and more recent ones such as TOD and DINO, and foundation model-based object detectors such as a grounding DINO and 𝗥𝗲𝗹. Okay, so now we look at the results. Let's start by looking at the results of a single source domain generalization setup for roads across climate zones. And here we first observe that there is a sharp performance drop for all the models. We see that those are built on foundation models such as grounding, DINO, and 𝗥𝗲𝗹 had a better OOD and ID performance in comparison to the other models. All right, so when we analyze the performance of object detectors under the multi-source domain generalization setup, the first thing that we see that multi-source training enhances not only the object detector performance on the ID test set, but also provides a substantial boost to the OOD performance. However, we still observe a drop in the OOD target test sets. Moving on to roads across the flooded regions. Since it's a data set that consists of 2 domains, we evaluated the performance of object detectors under the single source domain generalization setup. Here we see that there is a decline in the performance across both India and the US. And the performance drop exceeds 51% and 62%. And this kind of indicates that there is a significant impact of the domain-specific variations between the 2 regions. Now let's analyze the performance across hurricane events. Let's look at the single source setup first. Here we see that, consistent with the previous observation, the foundation model-based object detectors had the highest performance when it comes to OOD test set. And another interesting observation is that the object detectors had the weakest ID performance when evaluated on Hurricane Matthew. And this suggests that the data of this domain is naturally difficult and could suffer from factors such as label noise and class imbalance. Okay, so finally, let's have a look at the performance of object detectors on this data set under the multi-source domain generalization setup. And here we observe something quite interesting. Actually, the ID performance drops slightly under the multi-source when compared to the single source setup. And this suggests that the multi-source data adds more complexity, and it can confuse the object detectors. Also, we observe that there is still, and when it comes to OOD, there is an improvement in performance. Okay, so to summarize, RWDS is considered the first suite of domain generalization benchmarks for object detection, providing real-world challenging data sets to evaluate the robustness of object detectors. We've also observed that modern object detectors suffer under spatial domain shifts, including those built on foundation models. And when we compare the multi-source training to single-source training, we observe that training on diverse distributions enhances the generalizability of object detectors. With that, I'd like to thank you.